Welcome to Electromagnetism Part 2. In this video, we're going to take a look at the magnetic field created by a current-carrying wire. When you put this title into your notes, please pay attention to the capitalization and keep yours the same. Capitalized terms in these titles are going to be key variables that play in each of these discussions. So we take a look at here, we have magnetic field capitalized, and the symbol for that is capital B, created by a current, capital I, carrying wire. What's obvious here is that a magnetic field is created by when we put a current through a wire. What we're going to be talking about is how do you calculate the strength of that magnetic field, and how do you calculate, or how do you indicate the direction of that magnetic field? Let's start with the magnitude. That's the easy part. The strength of the magnetic field, it would be intuitive for us to understand that the magnetic field gets weaker the further we travel away from the wire. So one of the factors that control its strength is how much current you put through the wire and at what distance you are away from the wire. When we go to the reference table, we can see that the strength of the magnetic field for current carrying wire is mu naught over 2 pi times I over R. And I is the current going through the wire, and R is the distance from the wire itself. This term out front, mu naught over 2 pi, mu naught is the vacuum permeability, and that's 4 pi times 10 to the negative 7. And so you can see by division that this whole term turns out to be simply 2 times 10 to the negative 7. You'll often see that we just shortcut to subbing that in for this whole term right here. Okay, so that's a constant value, and then we multiply by the current divided by the distance we are from the wire itself. All right. Next, we are going to determine the direction of the magnetic field for a current carrying wire. And what you need to know here is that the magnetic field for a current carrying wire takes the shape of a circle or a cylinder three-dimensionally around the wire itself. So we have to come up with a way to depict that on a two-dimensional surface. And the way that we do that is we draw a circle that has a break in it, and the break in that circle indicates the part of the circle that is behind the wire. We always use conventional current in electromagnetism, and a conventional current is direction of positive flow. And so for this problem, our wire has been labeled to be connected on the left side to a positive terminal of a power supply, and on the right side to a negative terminal. So the conventional current, positive flow, would go away from the positive toward the negative. And so that's the direction of our conventional current. Now we have to come up with a way to indicate the direction of the magnetic field as it goes around this current carrying wire. And for this, we have what is called the right-hand rule. I'm going to pull this one up here, okay, to show a little bit better. You take your right hand, which we always use for positive charges. Our left hand we use for negative charges. And you stick your thumb out to the side, and your fingers naturally curl to form a C. Your thumb points in the direction of the current flow in this hand rule. Your fingers curl in the direction of the magnetic field around that wire. So if we take a look at this example, our current is actually pointing to the right, and so we point our thumb to the right on our right hand, and our fingers curl in the direction of the magnetic field around that wire. Behind the wire, that magnetic field, at the moment our fingers are going up. When we stop our fingers in front of the wire, our fingers are pointed down. And when we're above the wire, our fingers are pointed out of the page. As we discussed in video 1, the symbol for that is dot. And below the wire, our fingers are going into the page, and our symbol for that is X. So this is how we indicate the direction of the magnetic field for a current-carrying wire. What we don't want you to be left with a misimpression here is that it's just one circle. It's actually infinite number of concentric circles around the wire, with the strength being greatest near the wire and getting weaker and weaker and weaker away from the wire. And we'll have some problems that deal with this in the problem set as we go. All right, so that'll do it for this video, magnetic field created by a current carrying wire.